Hi. Today we're going to look at the problem of overfitting, which is that problem we saw last week that happens when the hypothesis we get from our model fits too much the training data and loses performance outside that training set. So first we're going to look at how to estimate the true error, which will be the error in general for all the future examples and not just the examples in the training set, and then how we can try to avoid overfitting. One way will be to select a model that doesn't allow hypotheses to fit so well, so it restricts more the class of hypotheses that we are using. Another approach is regularization, which is to change the way we're selecting the best hypothesis that our model can give in order to reduce overfitting by doing some changes in training. So let's look back at the last lecture. We saw that when we are fitting the parameters in our model to find the best hypothesis, we are optimizing some function. For example, when we try to maximize likelihood in linear regression, in the kind of regression that we saw, with those assumptions about where the error is, then this turns out to be minimizing the quadratic error. So we use this least mean squares minimization to obtain the best parameters. And if we have models that are more powerful, they will allow us to find hypotheses that can adjust better to the data. The problem, the way we did this with the linear models was to do this nonlinear transformation of our data. So we are basically reshaping our data into higher dimensions and bending it in a way. And then when we do a linear regression in these higher dimensions, we get something that is curved in our original space. So this allows us to create models that have more power to adjust to the data, so give us hypotheses that are closer to our training set, but this creates a problem of overfitting. If the power of the model is too much, the hypothesis will fit too well to the training data, and this sacrifices performance outside the training data. So basically this was the example we saw last lecture. If we use a very simple model, then we cannot adjust very well to the data. So with a straight line, we cannot fit these red points very well. But if we increase the power of the model, so if we adjust polynomial curves of higher degree in this example, we can adjust them to the points or even go too far and adjust them so well to this training set that we start getting suspicious results in some places, which will probably fail to predict correctly new examples. So let's see what we can do first to measure, to try to estimate how well our hypothesis is performing outside the training set. So last week we saw regression as obtaining the parameters by minimizing the error on the training set. This will be what we have to do, where we have a training set, a set of data that we're going to use to adjust the parameters of the models. So the parameters will always be adjusted using that training set. However, our ultimate goal, after we have the best hypothesis, will be to try to predict values for any example in our universe of possible values. So this U here is the universe of all possible examples that we can meet in the future. We're going to use this training set to find our parameters, but then we want to apply this hypothesis that resulted from this optimization, so the instantiation of all these parameters, in order to predict values for new examples. So we saw that the training error is measured in this training set, the set that we're using to optimize the parameters. And this is not a good indicator of the error we are going to get for new examples. The problem is that we are optimizing everything to minimize the training error, but in some cases, like we can see here, minimizing the training error means that the curve will go through as close as possible to all the points. But the result of that is that then we can increase the error outside the training set. So we cannot rely solely on a training error to get a good estimate of how our hypothesis will perform when we give it new examples that were not in the training set. So this is a problem. We cannot use the training error to estimate the performance of the hypothesis outside the training set. So now, how can we estimate the performance outside the training set for all the universe of possible points we can meet? The solution is to measure the error outside the training set. So this will give us an estimate of the true error, which is the actual average error the hypothesis will make over all the universe of possible points. So what we can do is to split our data into two sets. In this case, the blue dots were used to train the model, so to obtain this hypothesis, this curve here. And then the red dots were used to estimate how well this hypothesis performs outside the training set. So to give us an estimate of this true error. Note that we cannot measure the true error. So the true error is this expected error, the average error for all the universe of possible points. Since we don't have all the universe of possible points, we cannot measure the true error. But we can do an estimate. So if we split some points for testing and some for training, we train our model, so we fit the parameters using only these blue points here, and then we measure outside the training set, in this test set, and this gives us an estimate of the true error. But note that this estimate will change depending on how we assign points to the training set and to the test set. We do it at random. If we do it several times, we get slightly different estimates of the true error and slightly different curves because we have slightly different training sets as we assign at random our points to train and test. So this is an important concept here, an important idea, is that we cannot measure the true error, but we are taking a sample when we do this operation of splitting our data into training and test and then fit to the train data and evaluate the error on the test data. We are taking a sample of what a possible test error can be. So the idea is that this is an unbiased estimate of the true error because on average, if we were to repeat this infinitely, we would get a distribution like this. So sometimes we would get a higher estimate of the true error, sometimes we would get a lower estimate, but on average it would all tend to the real value of the true error. So even though each time we measure the test error, we are just taking a sample of possible values for these estimates, they are unbiased. It's an unbiased estimate because on average it will converge to the true error. So this is the basic idea. We are taking a sample of possible errors outside our training set by keeping a set of data, the test set, in order to measure the error after training our model. So these are the different concepts here. Errors that we can measure are the training error and the test error. The training error is measured on the data that we are using to fit the parameters of our model, and this is what we're actually trying to minimize as we fit those parameters. So this is why the training error is not a good estimate of how good the hypothesis is outside the training data. But then we can measure the test error. We set aside a set of points for testing and we measure the error on that set of points after training. And this gives us an estimate of the error outside the training set. Now, errors that we cannot measure are the true error. We cannot measure the true error, only estimate it based on these samples. And the generalization error, which is this error that is the difference between the training error and the true error. So it's the error that our hypothesis is doing when we jump from the data that was used to train the hypothesis to examples outside that data. Okay, so now let's see how we can measure and try to reduce overfitting using these measures and these concepts. If we look back at this kind of example, suppose we are doing this regression, we set aside a small set of points for testing, And now we try with different degrees of polynomials. So degree 1 is a straight line, degree 2, degree 3, and so forth. This blue line here is the training error. You can see that as we increase the degree of the polynomial, we increase the power of the model to adjust to our data, we start getting lower and lower training error, because now the curve can go closer and closer to the positions of the points in the training set. However, when we measure the error of our predictions outside the training set, we see this U-shaped curve here. This is approximately U-shaped. Note that each time we're doing this, we're taking a random sample from possible test errors that we will get depending on the data points we're using. So we have these fluctuations like this, but it's approximately a U-shaped curve because when the model is too stiff in this part, it's underfitting, it cannot fit the data correctly. So for example, this straight line will give us a large error on the training set, but also a large error on the test set. So this is bad on both sets because the model cannot adjust to the data. If we are on this side, this is overfitting because now the model is adjusting too much to the data. So even though the training error is very low, the performance outside the training set is very bad. And you can see this here where we have some approximations to the blue ones, but then some red ones. For example, this red dot here is very, very far away from the line because the line shoots all the way up there. So this is when we start getting this effect of overfitting when the error measured outside the training set starts to increase. We are now going too far, adjusting too far to the data. So one way of looking at this is to think about overfitting as an increase in the generalization error. So we are sacrificing our ability to predict outside the training set because we are adjusting too much to the training set. However, note that this is more a conceptual thing. The generalization error is not really what matters to us when we are selecting the best model, because what we really want is to minimize the error outside the training set. So this gives us one approach to try to reduce the effect of overfitting. We can see that not all models are the same. Some have lower training error and very high test error, others have high on both, others have lower values on the test error. But using this, we can now figure out how to choose the best model. So if we were to choose out of all these degrees of polynomial, we could look at these individual hypotheses as estimates of how the model can work when we train it with this data, and then see which hypothesis has the lowest test error. So this would tell us, for example, in this case, we could look here at degree 5 and we could choose to use the polynomial of degree 5, and this particular hypothesis seems to be the best one that we have in this case. So we could do this as an approach to select the best hypothesis that we train here and also the corresponding model, the degree 5 polynomial, by choosing the one with the lowest test error. But however, there is a problem when we do this. So each individual estimate of the test error, for example, this would be the chosen curve of degree 5. We have this estimate of the true error, which is given by the measure of the test error. So 0.027 something will be an unbiased estimate of the true error for this hypothesis. Unbiased means that it can be more than the true error, it can be less than the true error, but on average, if we repeated this infinite times, the average of these measurements would converge to the true error. So it's not biased either for upper values or lower values than the true error. But the problem is that we are not just measuring the test error. And this is something that usually is a bit confusing at first, but if we just measure one point here, this one could be above the true error or below. It's an unbiased estimate. This one could also be above or below, this one also, all of these. But if we now take all of these together and always pick the smallest one, we increase the probability of picking one that fell below the true error. So now the estimate becomes biased. So this plot illustrates this. Suppose that we have values with this distribution. This could be our unbiased estimates of the true error. The true error is somewhere here in the mean of these values. And if we do a single measure on the test error, we can get a value here or a value here at random, but on average they would converge to this mean value, which is exactly the true error. But if instead of just picking one, we roll the dice 10 times, for example, we sample 10 points of this curve and pick the smallest one, and if we repeat that, then the distribution we get is this one. It will be biased towards lower values because we are always picking the smallest of the 10. And this will give us a biased estimate. So this is one problem. If we do this, if our procedure is to measure the test error for different models or for different hypotheses, in this case, using different models and taking the best hypothesis, and then we pick the smallest value, we are biasing our estimate because we are increasing the odds of picking one that by chance happened to fall below the true error. So doing this procedure, picking the smallest one, will now make the estimate no longer unbiased. It's biased towards smaller values. So we cannot do this with the test error because the idea of the test error is to be an unbiased estimate of the true error. And if we are cheating by choosing the smallest one, we are making it biased and it's no longer a test error. It's something different that we're going to look here, which is called a validation error. And this is the basic idea. We're going to use three sets of data. We use the training set to adjust the parameters. We need this because we need to minimize some loss function, for example, the quadratic error, in order to find the best hypothesis that the model can give us. But then, at the end of the process, we need to have an estimate of how good this hypothesis is at predicting new values. So to do that, we use the test set to give us an estimate of the true error. But this has to be at the end when everything is done, because we cannot choose use the test error to choose something. If we do that, we are biasing the result. So we need this intermediate set here, the validation set, that does not belong to the training set. It's another set of data. So it allows us to do these measures here outside the training set. But then we are going to use those values in order to choose something. For example, to choose the best model that we're going to use. And so this makes the validation error biased, and it cannot be used to replace the test error. So this is the approach of validation and testing. We have a set of data to fit the parameters, another set of data to evaluate the error outside the training set, but which we are going to use to choose something, for example, the best model. And then at the end of the process, we have a final set of data that we did not use for any decision so far, that we're going to use now just to get an unbiased estimate of the true error. We're going to see a more sophisticated approach for this, because you see here, each time we do this measure, the actual measure depends on which points fell on the training set and which points fell on the test set. So we are getting just one estimate, but we could perhaps take several estimates and average things out. This is the idea behind cross-validation that we're going to see next week. But for now, we are going with this simple approach just to understand the concepts. So this would be the way to select the best model. In our case here, we would split into three sets. We would find the model with the lowest validation error, and then we choose the hypothesis that this model gives us as the best one, the one that minimizes the error hopefully outside the training set. Finally, at the end of this, we would use the test set just to get an estimate of what the error we can expect the error to be outside all this data that we used. Another approach to fight overfitting is regularization. In this first example that I showed with choosing the degree 5 polynomial, what I did was model selection, was basically selecting the best model, the one that allowed us to adjust to the data correctly, but did not overfit too much, so we could optimize the results like that. Another approach is to use regularization. Regularization does not change the model that we are using, but it changes the way we select the best hypothesis, so the learning algorithm, in order to reduce overfitting. I'm going to give a simple example, which is ridge regression. Ridge regression is a linear model. It's similar to what we saw so far, at least in this part, which is a linear regression where we are trying to minimize the quadratic error. So the difference between what the value, the output should be for each point, and what the output is. This is a function of the input values, the features, and the parameters that we have for our model. So in this case, this is a linear model, so these parameters simply multiply by the features, we add all the products up, and this is the function that we are using to produce all these different hypotheses. So the square of this error is the quadratic error that we saw previously, that we are minimizing, but in ridge regression we add a new term here, and this term is the sum of the squares of all our parameters. So these parameters are all the coefficients that we are using in our linear combination, and this sum multiplied by some scaling factor lambda. So basically what we're doing here is we are penalizing, remember that this is the function that we're trying to minimize, so we are penalizing our hypothesis if the coefficients are too large. So this will try to shrink the length of the vector of the coefficients as much as possible. And what this does is to constrain or to prefer hypotheses that have smaller coefficients. And this results in not allowing during training to so easily find a hypothesis that have very large values and that maybe adjust too much to the data, the training data, but then can go too far from what would be reasonable predictions. So let's see an example here. If we do this with these curves, remember that ridge regression is a linear regression, but we can do polynomial fits with a linear regression. All we need to do is to expand our x values and to include x squared, x cubed, and so on, and that way all the polynomial is simply a linear combination of these different powers. So if we adjust this data, we can see that with lambda 0, so this value set to 0, we are not regularizing, so we are just adjusting, minimizing the quadratic error, and we get this set of points here, this line here in blue, which goes very far from the data outside the training set. It goes very close to the training set, but then it makes a lot of errors. But even adding just a bit of regularization, so just 0.1 here on this lambda, we already have this green curve that behaves much better. And then by increasing lambda, we start getting the curve becomes more stiff, more hard to bend, and so it will no longer do these very far values here, reaching out too far, and it will be mostly constrained by these points and not going too far from the data. So by adjusting this parameter, we can try to find the best value that minimizes our error outside the training set. By validation, we can try to fine-tune this parameter. Okay, so let's see an example of these approaches. using this file that relates gross domestic product here, per capita, and life expectancy. This is for 190 countries, and we have these two values. So gross domestic product and life expectancy. And now we're going to try to see if we can find a relation between these two, the richness of the country, per capita GDP, and the quality of life measured in life expectancy. So this is how the data looks like. And one problem that we usually have to solve in practice is the range of values. Note that we have GDP can go very high, per capita GDP can go to 60,000 or something like that. And life expectancy is here in the range of about from 30 to 80 years. So we have very different scales here, and also potentially large values. If we are going to do things like expanding this to a higher degree, like a polynomial adjustment fit, for example, we have to do, for example, the x values raised to the power of 9 or 10, things like that. And if we have very, very large values, then we can have rounding problems when we try to add them with values that have that are much smaller, and so on. Also, if we use values that are very different from problem to problem, it's harder to fine-tune some parameters like regularization and so on, because they may need to change a lot from one problem to the other. So for both reasons, for numerical stability and the reproducibility of our approach and the intuition we have about these problems, it's always best to rescale our data in order to get things close to 0, between 0 and 1, or something like that. So we're going to see this in more detail in further along the semester, but for now we're just going to rescale everything to a scale between 0 and 1. So basically, since we are dealing with only positive values, if we divide all the GDP values by the maximum, then all the GDP will be between 0 and 1. And if we divide the life expectancy by the maximum value, the life expectancy will be between 0 and 1. We need to retain these rescaled, scaling factors, because if we are to use our model to, the final hypothesis to try to make some prediction, we need to convert it back into the appropriate units. So not only we need to feed into our hypothesis the x values, the feature values converted appropriately, but then we need to convert back the predictions in the correct units. So I'm going to skip that step, but just to remind you that when we do some scaling like this, for example, we load the data from this file. This is the file where we have the data. This is a tab separating the two columns. So we can use this function load_txt that we saw previously. We load the data, and we just specify that the delimiter is a tab character. So this will give us a matrix that has these two columns, GDP here, life expectancy in the second column. And now we can obtain the scaling factors by using from the NumPy library this max function for our matrix, and specifying that the axis is the first axis. So the first dimension is along the rows, and this means that the maximum operation will be done in this direction. It will be the maximum of this row and the of this column, so along the rows, and the maximum of this column. It's going to project in the direction of the rows. So this will give us two values, a vector of two values, which is the maximum of the GDP values and then the maximum of the life expectancy values. And we can do this operation because these objects, these vectors and matrices in NumPy are capable of doing broadcasting. What NumPy will do with these objects is to align the last dimension. So the last dimension in our matrix as a size of 2, because it's the columns, and it's going to align that with the last dimension of this vector here, which is its only dimension. A vector is only unidimensional, but it's also 2 because this vector has two values. So what this operation will do is to divide each row element-wise by the two values that we are giving. So this value will be divided by the maximum of GDP, this one by the maximum life expectancy, and then it will repeat this for every row. This one by the maximum GDP, this one by the maximum life expectancy, and so on. So NumPy makes it very easy to do this kind of manipulation with data because you don't need to use for loops or things like that. You just use broadcasting and apply the same operation to all the rows on the matrix. Okay, so this gives us our data rescaled by this scaling factor, and this scaling factor is the conversion between years and some arbitrary unit that we are using, so that our values go between 0 and 1, and also between dollars and the other arbitrary unit for GDP, so that GDP is between 0 and 1. And now we need to get 3 different data sets, one for training, one for validation, so that we can choose the best model, and one for test. To do that, when we are actually using, we'll be using the scikit library further on. So you will not have to code all these things by hand. But in the beginning, I will always show the details of the algorithms by showing a bit of code so that it's easier to understand and so that you have some reference where you can look at all the details. So what we can do here is we create an auxiliary function that splits at random some set of data into 2 sets, one with this number of points for testing and the other for training with the remaining points. And one way we can do this is this arange function is similar to range in Python, but returns an array. And if you give it just a number, it will return an array, a NumPy array with 0, 1, 2, and so on, and as many elements as the number you indicate here. So the number we are going to indicate here is the first element of the shape of data. Data is a matrix. The shape is a tuple with the length in all the different dimensions. And so the first one is the length along the rows. In other words, shape 0 is the number of rows in your matrix. So by doing this, we get in ranks a vector that has 0, 1, 2, and so on, and as many values as the number of rows in the matrix. And this is basically the set of indexes for the rows in the matrix. Now we're going to use, from the random model in NumPy, we're going to use this shuffle function that shuffles an array in place. So this will shuffle all the values in ranks, so they are now in some random order. And now we can easily split the data by using this Boolean indexing on the rows. So this compares these shuffled indices on the ranks vector with the number of test points that we want. And we'll output an array with the same size, but consisting of Boolean values, with a true value every time the rank is at least as large as test points or larger, and false if the rank is smaller than test points. So everything that is above test points gets a true value here, and since ranks was shuffled, this will occur at random along the rows of the matrix. And this is the set of rows of the matrix that we take out with all the columns. This is for the second dimension, we are choosing all the columns, and we select this set of random rows for the training set. And the remainder, so the inverse of this comparison, will be for the test set, all the rank values that are smaller than the number of points we indicate here. And the reason I'm using smaller here and not small or equal is because the indexing starts at 0 in Python. So if you want 10 points, the indexes are from 0 to 9. And so this way we get this number of points in the test set, and now we return the 2 sets. So this function allows us to split at random one matrix into 2 subsets of rows picked at random, and we can now use this twice to generate our sets. We get the training set of 90 points. We have 180 countries. So if we do the split using 90 for the second part, the test set, we get 90 for training and 90 in this temporary matrix here, that we can then further split 45 each way. So this is a general approach. We usually retain more points in the training set and fewer in the validation and test set. So in this case, 1/2 goes for training, 1/4 for validation, and 1/4 for testing. So 90, 45, and 45 points. And one thing that's important to note is that every time you run this code, different points will fall on the different sets. So the result you get will not always be the same. There is some randomness here because depending on which countries go on the training set, validation, or testing, you will get different results. This is something that we're going to do in the next tutorial. I deliberately put examples with few data points so that we can see this effect very clearly. In general, if you have large data sets, then this effect will not be very obvious because when you have a large number of points, this randomness effect will be small. So now we're going to find the best model. We are also going to find the best hypothesis out of all the models, but we're going to loop through the different models and try to find the one that gives us the best error outside the training set. But remember that since we are choosing the best one, we cannot use the test set because then the test, it will not be really a test error, it will be biased and not an unbiased estimate of the true error. So for that we're going to use the validation set. We can create here a function to compute the mean squared error so that we can evaluate the error on the validation set. And this is simply from one set of data in which we want to evaluate the error. We have the coefficients for the polynomial. We use the polyval function like we saw previously with these coefficients and the first column in our data. So this we assume it's the x value. And this gives us the predictions for the y. And now we take the mean of the difference between the predicted values and the actual target values that we have on our data. We square all those values. So when we do this on an NumPy array, it will broadcast this operation on all the elements of the array. So you get the square of each value in the array. And then we do the mean over all the array. So we get the mean squared error for our predictions compared to the actual value on that data set. And now we can do this loop here where we go from degree 1 through 8. Note that range stops 1 before the last value that you put here. And we fit a polynomial of that degree to our training data. So the x value is the first column, the y value is the second column. And now we have the coefficients for this polynomial. We use this function here to measure the error on the validation set. So we fit the polynomial on the training set, but then measure the error on the validation set. And now if this validation error is lower than the best one so far, then we keep this one, this validation error, this hypothesis, this set of coefficients, and the degree of the polynomial that we use. In order for this to work, we can just start with a very large number for the best error at the beginning so that the first iteration is guaranteed to be lower than that. And then we just loop through all the different degrees. And now at the end, once we picked the best one based on the validation error, we can now test it on the test set. So this is an important part, separating these two, because doing this, looping through all of them and picking the smallest one is going to give us a biased estimate because we are biasing towards the smaller values. And that's why at the end we need an additional set of data in order to get an unbiased estimate of what the error of this hypothesis will be. So now we can print this, the result. So this would be an example of choosing the best model, the best degree of the polynomial, and the best hypothesis of all these models by the the coefficients that we have here, by validation and measuring the error on the validation set. And then at the end, estimating the true error of that hypothesis using the test set. So this is an example. We have here for different degrees of the polynomial, different results that we have. The colors indicate training, validation, and test. And then we have here the validation error, the training error, sorry, and the validation errors. So you can see, not very well probably, but if you look closer later on the slide, you can see that the training error is going down as we increase the degree of the polynomial, but the validation error goes down to about 0.15 and then starts going up again, because now we are overfitting and we are losing performance outside the training set. So this way we can find the best degree 3 polynomial, and we reach the end and we have this result. Use a polynomial of degree 3. There are these coefficients that we trained on this training set, so we already have the hypothesis and we can then test it on the test set. Now, one thing here is that this depends a lot on the random split. So if you run this again, maybe it won't be the same degree, it will not be the same hypothesis, because it depends on which points are in the training set, the validation set, and the test set. And this I chose this example because this is really an extreme example. You have a country here, I think this is Qatar or something like that, that is very outside the normal range for the others. And if this one is in the training set, the curves are very different than what they are if this one is outside the training set. So this randomness of assigning the points to the different set can have a large effect on the results. So one idea would be to average different training sets and validation sets, and we're going to see that later on. For regularization, we can use ridge regression. We can do the same thing we are doing here, but instead of changing the degree of the polynomial, we can use a polynomial of very high degree, but try to stiffen the curve a bit with regularization. So let's use ridge regression. The scikit-learn library has a ridge class. We're not going to implement everything by hand, and we can use that to do ridge regression. Now, ridge regression is a linear model, so we cannot do curves in the space where we are fitting our model, because it's just a linear combination of all the input values. But we saw last week how we can overcome that shortcoming by changing, projecting our data into higher dimensions and bending our data. So this is what we can do here. We can create this function to expand to some degree that we want. So let's assume that we receive a data matrix that has the x value in the first column and the y value in the second column. And now we're going to create a matrix that has x, x squared, x cubed, and so on, and increasingly until the degree that we want. So we're going to create this new matrix by using this zeros function from NumPy, where we specify the number of rows and the number of columns. So the number of rows is the same as the original matrix. The number of columns is the degree that we have plus 1, because we also need the y value on the matrix, the target value that we want. So the first column of this new matrix will be the original x values, so the ones in the first column on the original data matrix. And the last column of our new matrix will have the y values, which are at the last column of our data. Note that you can use negative indexes in NumPy or in Python in general to count from the end of the array. So this index -1 is the last index, regardless of how many columns we have here. And now for each, from the second degree all the way to the last one that we have here, so that's why I added 1 to include the last degree here, we're going to put in the corresponding column the original x values raised to that power. So on column of index 1, we'll have x squared. On column of index 2, we'll have x cubed, and so on. Remember that column of index 0 is the original x values. So after we do this, if we do a linear regression with these features, we are actually doing the same as a polynomial regression with the degree specified, because it's just a linear combination of all these powers of x. So we load the original data, we rescale everything to between 0 and 1, like we did before, but now we're going to expand this to 10 degree 10, so we have a polynomial of degree 10, and we split into train, validation, and test. And now we do the same thing that we did with the polynomials, but we are not going to do a polynomial fit with different degrees. We are going to use ridge regression from scikit-learn. So from this linear model module, you can import the ridge class. We create this ridge class, and we are going to give here this alpha value is the weight given to the regularization factor. So the one I have lambda here in this equation, in the documentation, in the function, they call it alpha. So by changing this, we change how much the regularization factor weighs on the loss function. And so if we increase this lambda, we make the curve stiffer. If we decrease it, it's easier to bend and to adjust to the data points. So this is what we have here, the result. As we do this loop, we create this solver for the ridge regression. This is, you have different options. This is just to illustrate different options that we have here for the exact solver. You can look up the documentation. This shall ask you is to solve the problem with a closed formula, so it's not an iterative process. It's faster in this case, but it may not work with all data. This is the tolerance for the computation, the numerical tolerance for finishing the computation. And then when we have this object, we call the fit method to fit the parameters. So we give the training data, which is as features, as the x values. We give every column except the last one. So this is this column -1 means all the columns of the matrix except the last one. And then the target value, the y value, is the last column on the matrix. And now we call the predict method of the solver after fitting in order to predict the values for the validation set. And now we can compute the mean quadratic error, which is what the predicted values are and what the predicted values should be, because we're going to take the y values on the validation set. So the mean of the square of these errors gives us the mean quadratic error, and again we can choose which value for the regularization is best. For this loop we can use 50 points. Linspace by default gives you 50 points between the intervals. If you add a new argument, for example, if you wanted to divide this into 100, you could add an extra argument like this. But in this case, I chose 50 points between these two extremes. And if we plot the validation error in this range, we have this result here. So we can see that with the very low regularization, the curve is too easy to bend, so we start to get a large error on the validation set. As we increase regularization, this validation error decreases, but then it starts to increase again because now the curve is too stiff to adjust to the data properly. So this way we can pick the best value for the regularization parameter using the validation set, and it's the same idea as we did for model selection. The big difference is that in this case the model is always the same. We are always using this ridge regression with 10 with these 11 features equivalent to, no, with these 10 features equivalent to a polynomial of degree 10, but we are changing the lambda here, the weight of the regularization. And so we are changing the stiffness of the curve in order to optimize the prediction outside the training set. So this is the result here. We are using a polynomial of degree 10, but with regularization, it's stiff enough not to go very far from the data. So to sum up this lecture, we have these error measures that we use to estimate the true error. So the training error is the one that we are measuring on the training set to adjust the parameters. This is not really a good estimate of the true error because it's very biased by all the training process. The validation error is measured outside the training set, but it's measured because we also want to optimize some other meta parameter. For example, we want to select the best model, or we want to select the best regularization factor. And since we are doing this several times and choosing the one that gives us the smallest error, this will also be a biased estimate of the true error. So we cannot use it really to estimate the true error. We can use it just to optimize some choice there. So finally, we have the test error. This is also measured outside the training set, but it was never used to choose anything. So it remained unbiased, and it can give us an unbiased estimate of the true error. Remember that all these estimates are stochastic. We cannot measure the true error unless we have all the universe of data points, and we usually don't. But the idea is that if we are not using those values to choose anything, the estimate will be unbiased. And we saw these two approaches to try to mitigate overfitting, which is selecting the best model and using regularization to change the way the hypothesis is selected. So I recommend that you read the section 3.1 of Bishop's book and Alpiden 2.6 through 2.8 about this subject matter. And also you can take a look at the documentation on scikit-learn for the linear model module. This is not something for you to read or memorize, but just take a look, because when you're doing this in practice, it may be useful to go to the documentation and check the options that you have there. So let's take a short break, and I'll resume the second lecture at 5 o'clock.